All right, so this is problem 5 from this week's problem set. It's kind of a classic problem, and someone had requested it, so I just wanted to do it a couple different ways, and hope you enjoy. So this is problem 5. It says counting every possible square of each size from 1 by 1 to 5 by 5. What is the total number of distinct squares which can be traced out along the lines of the accompanying grid? And I guess in short, this question is asking how many squares are there in this 5 by 5 diagram here. So these actually show up on Facebook, and you can watch people's posts. But so I'm going to give you 2 ways you could do this. The first way I'm going to show you, or the way I would think about it, is called the corners method. So every square has an upper left corner. So I'm going to note that, for instance, this, I'm going to use a brighter color, I think. Let's use green. So, for instance, that corner right there can serve as the upper left-hand corner of a square, whereas this right here cannot. So I'm just going to go through right now, and I'm going to highlight all of the intersections that could serve as the upper left-hand corner of at least one square. So everything I'm highlighting here could be the upper left corner of a particular square, of at least one square. And the reason this makes this problem more manageable is we're going to quickly be able to count the number of squares that have certain intersections as the upper left-hand corner. So for instance, this bottom right square is the only square that has this as the upper left-hand corner. So I want to put a 1 there. This upper left corner here can only serve as the upper left-hand corner of one square, and that's this one. Same here. This intersection here only serves as the upper left-hand corner of one square. So I'm putting 1s in all of these places because all the upper left-hand intersections can only create one square for each of those. Now let's focus on this one here. That intersection can serve as the upper left-hand corner to how many squares? Well, one of them is this 1 by 1, but the other one is this 2 by 2. So that intersection serves as the upper left-hand corner for 2 distinct squares. So I'm going to put a 2 there. And what you'll notice is if you think about doing the same reasoning for this intersection, that can serve as the intersection to this 1 by 1, but also this bigger 2 by 2. So each of these, you quickly see, right, you're going to have 2s in that next layer. For the similar reason, these are going to be 3s, these 4s, and this a 5. Okay, and now all you need to do is add up all these numbers. So you might add up the rows first, and then sum down. So 5 plus 4 plus 3 plus 2 plus 1 gives you a 15. 4 plus 4 plus 3 plus 2 plus 1 will give you a 14. This gives you a 12. This gives you a 9. And then this last one gives you a 5. And if you add those up, you get your answer, which is 55. So I shouldn't have written 15. 55. So I'm going to show you another way to do this problem. This is probably a little more conventional. And that way would be to count the total number of 1 by 1 squares, the number of 2 by 2s, 3 by 3s, 4 by 4s, and 5 by 5s. So to be systematic about it, let's first count the number of 1 by 1s. So going down the side, the number of 1 by 1 squares can be found by multiplying 5. 1, 2, 3, 4, 5. I'm kind of indicating the sides down here. 5 times 5, because, for instance, the intersection of that top with this side is this square here. So every pairing of a top with a side creates a square. So to get the total number of pairings, you multiply. So there are 5 sides times 5 tops. That's 5 squared. So that's the number of 1 by 1s. Now the number of 2 by 2s, let's go across the top first. So there are 2 by 2 squares that have this length here as a top, right? And I'm referring to those 2 squares there. There are 2 by 2s that have those 2 sections as the top. There are 2 by 2 squares that have these 2 sections as the top, and there are 2 by 2 squares that have these 2 sections at the top. And similarly, if we go down the side, there are 2 by 2 squares that have that as a side, that have those 2 as a side, that have those 2 as a side, and then have those 2 as a side. So every intersection of a top with a side will create a square. So for instance, this intersected with this precisely creates this 2 by 2. There are 4 sides, there are 4 tops. 4 squared are the number of 2 by 2s. And you might be able to kind of induce what's going to happen here. Right now, counting the 3 by 3s, we use similar reasoning. I'm going to go across the bottom and the right side just to save space. So a 3 by 3 could have this as a bottom, right? That as a bottom. Could have those 3 representing a bottom. And lastly, it could have those 3 representing a bottom. And across the side, 3, 3, and those 3. So that side intersecting, for instance, with this bottom would precisely refer to this 3 by 3 square here. So the number of 3 by 3 squares are the number of sides times the number of bottoms, which is 3 squared. And I think at this point you can figure out what's going on. So when you add up the sums of those squares, there is a formula for this, but it's probably easier just to add them up. You do end up getting 55, which of course is our answer.